You've probably seen footage of an icebreaker pushing through Arctic ice. The ship looks unstoppable, carving a path through pack ice that would trap any normal vessel for months. The bow slams forward into white sheets of frozen ocean, and the ice shatters in chunks the size of cars. Everything about the visual suggests brute force, a battering ram using weight and power to smash through a barrier. That mental image is wrong. Icebreakers don't ram through ice like a bulldozer hitting a wall. What looks like a head-on collision is actually a climb and crush using geometry borrowed from 11th century Arctic fishermen who had no idea they were solving an engineering problem that wouldn't be formally understood for another 900 years. The mechanism is hiding in plain sight, but unless someone points it out, your brain fills in the wrong explanation automatically. Normal ships have pointed bows designed to slice through waves and minimize drag. The bow cuts the water cleanly, parts it to the sides, and lets the hull glide through with minimal resistance. In open ocean, this works perfectly. In ice, it's a disaster. Ice isn't water. It doesn't part and flow around the hull. It resists, pushes back, and if you ram it straight on with a pointed bow, the force concentrates at a single spot. The bow might punch through thin ice, but anything over a foot thick will stop the ship cold. The pointed shape that cuts through waves so efficiently becomes a wedge, jamming itself into a solid barrier, transmitting all that impact force directly into the hull structure and the propellers behind it. The ship loses momentum, the ice doesn't break cleanly, and broken chunks pile up in front of the bow, creating a wall of debris that makes forward progress even harder. This is what early polar explorers discovered the hard way when they tried to use conventional ships reinforced with extra planking and iron bands. The reinforcement prevented the hull from being crushed when the ice closed in around them, but it didn't help them move through the ice. Ships got stuck, drifted with the pack ice for months, or worse, got squeezed until the pressure popped rivets and cracked wooden planks. In 1845, British explorer John Franklin led an expedition into the Canadian Arctic with 2 ships reinforced exactly this way. Both ships became trapped in the ice near King William Island. The crews abandoned ship and attempted to walk out. All 129 men died. The wrecks weren't found until 2014 and 2016, still locked in the ice where they'd been trapped 170 years earlier. Icebreakers don't fight the ice head-on. They climb on top of it, then use their weight to break it from above, the way you'd step on a frozen puddle to crack it. The hull isn't designed to pierce through ice. It's designed to ride up onto the ice sheet and crush it under tens of thousands of tons of steel. The bow of an icebreaker slopes upward at a shallow angle, typically around 20 to 25 degrees from the keel line. This creates a ramp instead of a knife edge. When the bow contacts the ice, instead of hitting it straight on, the sloped shape redirects the force. The ship's forward momentum, combined with the engines pushing from behind, drives the bow up onto the surface of the ice sheet. The ship literally climbs out of the water. As the bow rises, more and more of the ship's weight transfers from the water onto the ice. A modern nuclear icebreaker like Russia's Arctica weighs around 25,000 tons when fully loaded. That weight pressing down on a relatively small area of ice creates stress the ice structure can't handle. Sea ice has high compressive strength when force is applied from the sides, which is why pack ice can squeeze and crush a ship trapped between 2 floes. But ice has low bending strength when force is applied from above. It can't flex. It snaps. The ice beneath the bow fractures in jagged lines radiating outward from the point of maximum stress. You hear it crack with a sound like a gunshot, sometimes multiple cracks in rapid succession as the failure spreads. The broken pieces tilt and shove against each other as the ship's weight continues pressing down. Then the bow breaks through completely, and the ship drops back into the water with a massive splash, pushing the broken ice aside as the hull slides forward. The hull shape does something else critical here. An icebreaker's hull is widest near the top of the waterline and narrows as it goes deeper. This inverted profile means the ship is wider at deck level than at the keel. When the broken ice tries to close back in around the sides of the hull, the shape forces the ice to ride up instead of crushing inward. The ice gets pushed up and out, clearing itself away from the ship rather than piling up against the sides and increasing friction. This works for ice up to about 8 feet thick. Anything thicker requires ramming. The ship backs up several hundred feet, then drives forward at increasing speed, using the run-up to build momentum before the bow climbs onto the ice. The ship hits, rides up, and the ice cracks, but doesn't fully break. The ship settles back. The captain reverses, backs up, and repeats, targeting a slightly different section or hitting the same spot from a different angle. Each impact weakens the structure until the ice gives way. This can take hours. For multi-year ice over a meter thick, a single breakthrough might require 10 or 15 ramming attempts. The ship advances a few dozen meters, then does it again. An icebreaker rated to move through 6-foot ice at 3 knots might take an entire day to cover a mile through ice just 2 feet thicker. When ramming isn't enough, there's a backup system. Many icebreakers have massive ballast tanks along the port and starboard sides. Pumps can transfer thousands of tons of water from one tank to the other in under 3 minutes. When the ship gets stuck, friction locking broken ice against the hull, the crew activates the ballast. Water floods from port to starboard. The ship heels over to one side. Then the pumps reverse, rocking the ship back. The hull's shape, wide at top and narrow at bottom, acts like a wedge. As the ship rocks, it shoves the ice away, breaking the friction lock. The rocking motion looks comical from a distance, this massive ship swaying like it's dancing. But each shift represents hundreds of tons of weight moving laterally in seconds. If you were standing on deck, you'd feel the entire ship tilt under your feet, then snap back, repeating until the ice breaks free. The numbers behind these ships are extreme enough to feel implausible until you see one in person. Russia's 50 Let Pobedy, one of the most powerful icebreakers in service, generates 75,000 horsepower from its nuclear reactors. For comparison, a typical cargo ship of similar size might have 30,000 horsepower. The difference isn't for speed, it's for sustained force. Breaking ice requires continuous power output at levels that would overheat and destroy conventional diesel engines within hours. The hull plating at the bow can be 48 millimeters thick, nearly 2 inches of high-strength steel engineered to stay tough at temperatures where regular steel becomes brittle and prone to fracture. Between the inner and outer hulls, there's often a layer of water ballast acting as a shock absorber, distributing impact forces across a wider area to prevent localized stress fractures. The propellers are among the most vulnerable components on the ship. They sit at the stern, where broken ice constantly scrapes past at high velocity, like grinding wheels made of frozen seawater spinning against metal blades. Propeller blades on icebreakers are thicker, heavier, and more rounded than on normal ships, designed to take repeated strikes without shattering. Some advanced icebreakers use azipod propulsion, electric motors, in pods that can rotate 360 degrees, allowing the ship to break ice while moving backward with the same efficiency as moving forward. This turns the ship into a bidirectional icebreaker that can reverse course without turning around, cutting maneuvering time in half. But all these features that make icebreakers effective in ice make them terrible in open water. The rounded hull that prevents ice from crushing the ship sideways also makes the ship roll heavily in even moderate seas. There are documented cases of powerful icebreakers taking shelter from summer storms in the Arctic because the rolling motion became so severe it threatened crew safety and equipment. A ship designed to smash through meter-thick ice can't handle 3-meter ocean swells without rocking like a bathtub toy. The flat, sloped bow that climbs onto ice doesn't cut through waves. It bounces over them, slamming down on the far side of each swell and sending shockwaves through the hull. Crews describe it as riding in a vehicle with no suspension over a washboard road, except the vehicle weighs 25,000 tons and the road is the North Atlantic. This is why some modern icebreakers are built to operate primarily in reverse when breaking ice. The stern is designed with a steep icebreaking profile, while the bow uses a more traditional pointed shape for open water transit. The ship travels bow first through open ocean, then rotates and breaks ice, stern first, when it reaches pack ice. It's a compromise, sacrificing some ice-breaking power for better handling in normal conditions, but for ships that have to transit long distances between ice zones, the trade-off makes sense. Icebreakers exist because entire economies depend on them. Russia operates the largest fleet of icebreakers in the world, including the only nuclear-powered ones, specifically to keep the Northern Sea route open. This Arctic shipping corridor runs along Russia's northern coast from the Barents Sea to the Bering Strait, cutting shipping time between Europe and Asia by thousands of miles, compared to going through the Suez Canal. In winter, the route is completely impassable without icebreaker escorts. Cargo ships gather in convoys, sometimes a dozen vessels trailing behind a single icebreaker, like ducklings following their mother, using the channel the icebreaker carves. If the icebreaker stops, the entire convoy stops. If the icebreaker gets stuck, which happens more often than most people realize, every ship behind it gets stuck too. In November 2021, more than 20 ships became trapped in ice along the Northern Sea route when an early freeze caught them by surprise. Russia's most powerful nuclear icebreaker, the newly commissioned Arktika, was deployed to free them. It took nearly 3 weeks. Some ships were stuck for over a month before they could be escorted out. These weren't small boats. They were cargo vessels carrying construction equipment, food supplies, and fuel to remote Arctic settlements that depend entirely on seasonal shipping for survival. The United States Coast Guard operates icebreakers to keep resupply routes open to McMurdo Station in Antarctica, a research facility that would be completely cut off without them. Every year, an icebreaker has to break a channel through sea ice thick enough to support the weight of vehicles, clearing a path for fuel tankers and cargo ships carrying everything the station needs for the year. If the icebreaker fails or gets delayed, the station runs out of supplies. Canada uses icebreakers in the St. Lawrence Seaway and on the Great Lakes to keep shipping lanes open during winter, when ice would otherwise shut down ports critical to the region's economy. Without them, cities in the interior would lose access to bulk cargo for months at a time. Icebreakers sometimes need to be rescued by other icebreakers. In February 2026, a German icebreaker got stuck while attempting to rescue a trapped gas carrier. The only vessel powerful enough to free both was a Russian nuclear icebreaker, but sanctions complicated whether the rescue could proceed. The ships sat motionless for days while governments negotiated. This happens because icebreaking capability is rated for specific conditions: flat ice of a certain thickness, under certain temperatures, in certain sea states. Real ice doesn't follow ratings. Multi-year ice forms ridges where flows collide and pile up, creating walls 15 or 20 meters thick. Wind-driven compression creates pressure zones where ice locks together so tightly that even climbing onto it doesn't generate enough force to crack it. When conditions exceed design limits, the ship waits, sometimes for weeks. In November 2021, over 20 ships became trapped along Russia's Northern Sea route when an early freeze caught them by surprise. Russia's most powerful nuclear icebreaker took nearly 3 weeks to free them. Some ships were stuck for over a month before they could be escorted out, carrying food and fuel to Arctic settlements that depend entirely on seasonal shipping. The earliest icebreaking vessels were Russian coke boats built in the 11th century for the White Sea, which stays frozen over half the year. These small wooden ships had rounded hulls, so that when ice closed in, pressure would lift the boat onto the surface instead of crushing it. The design came from generations of Arctic fishermen who noticed certain hull shapes survived and others didn't. The first modern icebreaker was Russia's Pilot in 1864. The designer copied the 20-degree bow angle from old fishing boats, added a steam engine, and discovered it worked. By 1957, the Soviet Union built Lenin, the world's first nuclear-powered icebreaker. The nuclear reactors gave unlimited range and continuous high-power output. Lenin operated for 30 years and covered over 650,000 nautical miles, most of it through ice. Modern nuclear icebreakers can theoretically operate for 70 years without refueling. They represent a technology path that started with fishermen carving rounded hulls into wooden boats and ended with 25,000-ton ships powered by nuclear fission using the same hull geometry for the same reason. The same physics that lets an icebreaker crush sea ice explains why frozen lakes crack under your weight. Ice can support enormous lateral pressure, enough to crush a ship between two flows, but it can't handle concentrated downward force. Your weight over the soles of your boots creates stress the ice can't distribute. It snaps. An icebreaker's hull is a wedge exploiting a structural weakness. The ice doesn't break because the ship is stronger. It breaks because the ship's shape redirects force in a way the ice can't resist. You can watch hours of icebreaker footage and see this happening. The ship doesn't slam and blast through. It climbs up, tilts forward, and drops through, every time. The bow rises just before the break. There's a moment of suspension, then the sudden drop back into open water. It's not ramming, it's leveraging geometry and weight to break material along its natural failure plane, using principles that Arctic fishermen understood 1,000 years before anyone formalized the physics. If you had to design a ship to break through ice, would you make it climb on top and crush down, or try to build something that rams straight through? Leave your answer in the comments. If you enjoyed this, hit the like button and subscribe for more videos like this.